Hello and welcome to They're Just Robots, podcast on robotic control, brought to you by Enforced Social Isolation and Harun Sheikh.
Thought you had plenty of friends, more than you could ever really want, but really sometimes they're not what you need. They can't do it all, cause they're only human. True kind of pal would drop all that she's doing. You need a true friend, and we've got lots. They're just ROBOTS robots.
Hi and welcome back. This is episode 8 of They're Just Robots, our WE413 podcast. Today, we're focusing on centralized motion control featuring force control. The issue of centralized versus decentralized control is not just limited to robots. I mean, look at the current situation with COVID-19. There's a definite difference between centralized and decentralized approaches in controlling the spread. In a decentralized case, every local controller is for itself. So whatever comes, whatever bus, airplane, whoever arrives into this local community is considered a disturbance, a surprise, something that needs to be taken care of in a certain controllable way. While in the centralized case, it was probably already accounted for because it was seen from the top. And obviously, both approaches have their merits, and both approaches are being used in different places. And only time will show what works better and what intended and unintended consequences of centralized versus decentralized control are in this particular case. Of course, I'd argue that this control problem is much harder than those that we're covering in this podcast. So without further ado, let's go back to our robots. As we already said last time, the centralized control is one of multiple input, multiple output systems, and one of nonlinear systems, in the sense that we do not try, at least not all the time, to decouple the system into small linear systems that can be handled joint by joint. Instead, all of a sudden, we know everything about our manipulator at all times, everything about its structure, about inputs. We can produce all the outputs from a centralized place. We get great power, but also great responsibility. In today's story, we'll keep on going back to two basic centralized algorithms. One of PD control with gravity compensation, and the other of inverse dynamics. So whatever we're doing, we're going back to these two as the basic schemes. Not to change everything abruptly, we're still in the same realm we were in the previous podcast, the one of joint space. So we'll shift to the operational space a bit later. So we're still observing everything in terms of the angles, in terms of the robot itself. So now our whole robotic manipulator is described by a pretty big differential equation, one in matrix form with certain elements that are performing coupling between different joints. So it's not just a diagonal form, let's say. Hence, we can't rely on splitting it into more scalar equations. We have to stick to the vector one. But that doesn't prevent us of thinking in terms of our regular control theoretic schematics now. So our inputs are still positions and velocities. So position and its derivative. And as you know from your control background, if you take the variable and its derivative and use both for control, sum them up with certain gains and see how that affects your feedback loop, well, you have a PD controller. And the advantage of a PD controller is that it's fast. It's very fast because the derivative component is gonna see the change before it happens because it sees the rate. As such, PD control is very suitable for a problem in which you're trying to achieve something called constant equilibrium posture. A constant equilibrium posture is essentially a particular configuration in space you want your robotic manipulator to assume. Now, even if your robot is the only thing that exists in the universe, we still have to be realistic and add some force of gravity in there. So it's not the only thing in the universe, I suppose. It's your manipulator and the Earth below it. So you can't really go wild about the configuration you want to assume. Sure, you can, but then you have to keep on compensating for the gravity effects. So your PD controller will be able to keep you in that position. So if some disturbance happens, if you slip slightly, you'll go back into the configuration, but you need another component. You need a component that will model the behavior of your manipulator subject to gravity, and then you just cancel it out. So that's why we call it PD control with gravity compensation. It has a PD controller, but also it has a gravity compensator, which is just calculating the gravitational term in your big differential equation and then subtracting it out so that you're left with a gravity-less universe. Sure enough, if you know everything about your manipulator, if you have a perfect model of it, you should be fine. But what if you don't? What if you have, let's say, an uncertain load that you're holding at the end effector of your manipulator? Then all of a sudden you have an issue. You can't really do proper gravity compensation. You can't afford an integral component because of time and everything. So what about this static error you're getting? That's where you start thinking about workarounds, about the ways to make your centralized control, in this particular case PD control with gravity compensation, a bit more resistant to these uncertainties all around you. And that's a complete different topic we'll come back to a bit later. So for our second big paradigm of the day, we go to inverse dynamics. The scheme of inverse dynamics control in centralized motion control is pretty much that of exact linearization through nonlinear feedback. So you're not really trying to approximate your system with a linear one, but you're actually producing an exact linear system out of your nonlinear system. This is where you should say, okay, that's impossible. And sure enough, it probably is, but again, we have a trick. Lump nonlinear things together and make everything else linear in terms of that nonlinearity. In this particular case, it's the input. So you lump the nonlinearities in the input and everything else will remain linear with respect to that one. And not only linear, but also separable. So you'll be very happy to see it all decouple and you'll be able to do your calculations in parallel again. Now the thing is, it's not really the scheme we saw before with the feed forward, in the sense that we don't calculate most of the things in this scheme beforehand, but we have to do it online. It's because of the nonlinear feedback. We don't know what it's resulting in. We don't have the invariance we had before with everything being linear in the decentralized and semi-decentralized case. So that pretty much means that the inertia matrix and Coriolis, centrifugal, gravitational, and damping components, they all need to be calculated online all the time. Now that sounds like a lot of work to do, and it really is. If you do things online, that means that you have to do them before the next time instant of your control comes. So if you're ready, if you have all the data calculated for your control to get to the next instant, you go. If you don't, you're in a lot of problems because at this point, you don't have all the calculations done. You don't have everything worked out. You don't have the exact information about the system. And sure enough, these schemes rely on the exact information. I mean, that's why we're doing it centralized anyways, to have the big picture and to calculate everything in. So now that we have this perfection sorted out, at least in the sense that we're aware that we can't really have it, let's discuss how do we go about it. The two basic avenues are those of robust control and adaptive control. They both deal with uncertainties and imperfect models, but in two essentially different ways. And sure enough, they both constitute fields of research on their own, so we're just going to be very brief here. Robust control is all about expecting the unexpected and making sure that whatever happens, whatever disturbance and uncertainty hits us, we're still on the right track. While the adaptive control is assuming that we don't really have a good model in the beginning, but that as time progresses, we should get better. In the robotic case, in the case of schemes we discussed before, adaptive control has this issue of what if we don't really have a good structure of the model? Because you see, adaptive control is all about adapting the parameters of a given model. So if you have the components of the model well designed in the qualitative sense, you should be fine. But what if you skipped a particular component of the dynamics? You didn't model it at all. Your adaptive system will try to cram all the dynamics that are observed in the wild into your bad model, and hence it will produce something that corresponds to reality in no way. So adaptive control is great as long as the model has all the bases covered. It doesn't have to be exact, but it has to have all the dynamics. On the other hand, robust control couldn't care less. And that's the tricky part about it. Because if it doesn't care about the physicality of your system, it could well produce some strains and some very unphysical inputs to your system and maybe break down your mechanics. So there's another thing to think about. And speaking about breaking things, it's time to start talking about force control.
That dog is man's best friend. That might very well be true. But every bone that a canine bears, but to do better, steadfast and truer. Fetch any stick, bring your papers, slippers, available in fur, and they don't need wax, they're just ROBOTS rollers.
As a preliminary to the story of force control and the story of interactions of your manipulator with the environment, we first shift to the operational space as promised. So all of a sudden, instead of thinking in terms of angles and everything that's natural to our robot, we start thinking of the elements that are natural to us and natural to the environment we exist in. So all of a sudden, the control system is handling constraints given in the operational space. So Cartesian space, say. One approach you could take is, of course, keep on taking whatever is given to you in operational space, doing inverse kinematics to it so that you get everything translated back to the joint space and keep doing whatever you were doing before. Let's just say that's very suboptimal for most applications. So why not do control directly on the operational space variables? Because we'll have to do it anyways when our robot enters the real world, the environment, since the environment doesn't really translate well into joints. In a basic scheme of things, it's again the story of your regular position feedback. You collect the position in operational space of your manipulator, compare it to the position you're trying to achieve, and you get a certain difference. That difference is your error. And if that error is small enough, sure, you can just translate it directly into your error in joint space by using a Jacobian inverse control system. All the schemes based on Jacobian inverse control will have a lot of Jacobian components around. You'll be calculating back and forth in your feedback loops, but that doesn't make it the stupid scheme, the basic scheme of recalculating everything into joint space, doing everything in joint space, and then going back to the operational space and so on. But you do it all inside of your loops, not on the outside. And again, you can do your whole PD with gravity compensation or inverse dynamics. Both work in operational space control as well. And conceptually, it's as basic as replacing your cues with your axis. So your angular measurements with the operational space Cartesian measurements. However, do bear in mind that as soon as you have Jacobian in the story, you have the issues of singularity and redundancy. So you have to make sure that your robot doesn't end up in an impossible position, doesn't end up in a position it can't go back from, and all the usual problems you had in your previous dynamics courses. But enough about the harm that the robot can do to itself. Let's get it into the real world and let's have it bump into things and see what happens there. So if a robot is in an environment in which there is a possible interaction of it with it, your motion control might have serious issues. First of all, you're probably not going to do joint control. And if you're not doing joint control, you're not doing decentralized control. Hence, you're doing a centralized control algorithm. And with centralized control comes a lot of information about the model you need to have. And then again, you may know a lot about your robot, but you probably don't know every little thing about the environment. Environments tend to change. Environments tend to be rough around the edges. And they tend to be very narrow sometimes, very dangerous for your robot. So to keep it safe, don't really do motion control when you have an interaction with your environment, because the models won't fit. Let's do something smarter.
cut your hair and look after your mother. Make your soup when you're sick of all the things that to a person or a bother. Take out the trash and vacuum your carpets. Listen to you when you're sad and confused. Give you directions when you're lost. They're just R-O-B-O-T-S rollers.
You may remember that we discussed this right in the beginning of our course. You have a great plan for a task you're about to perform, but somehow you miss. There's something in the environment you didn't expect. The screw wasn't aligned with the hole. The ground wasn't exactly where you expected it to be. So what happens then? Your control algorithm needs to take care of that particular mishap. And hopefully it's not an unstoppable force hitting an unmovable object. So one will surrender. Will it be the robot? Will it be the environment? Will it be both in a ratio? That's the issue of compliance and stiffness, and of control that uses compliance and stiffness to achieve a particular behavior of the robot. For the sake of the argument here, let's just think of everything as a spring. Everything is a spring if you look hard enough, and everything has a certain compliance. Everything gives way to an extent. And there are different ways it can give way. So if we speak of passive compliance, we can describe it in terms of scalars and matrices, and depends on the scale you're talking about. But there are always translational, rotational, and coupling terms, both in compliance and in its reciprocal stiffness. So your two rigid bodies that are connected in some way, so again, a spring-ish story, they have the ability to comply or to stay stiff in a translational way, in a rotational way, and there's also almost always a relationship between the two. So they're not usually independent. But sometimes you really want them to be independent. As you may remember our case when we did the RCC, remote sensor compliance. It relies on the concept of passive compliance and it decouples your translational and rotational compliance, in the sense that all of a sudden you have a compliance in one direction but not in the other. And that's pretty much what we want with compliance control. We want to be able to surrender in some ways, but keep going in other ways. So don't allow the environment to control us completely, but to have our say in the particular task we're doing. If we're stiff in all directions and all the ways, we're probably going to break something if the environment is stiff too. And then again, if we're compliant in all ways and directions, and the environment is compliant too, probably nothing will ever get done. So what we can do is make a mechanical structure that will have certain compliance properties, certain physical compliance properties, like RCC does, or make something that will keep changing the compliance and stiffness of our entire system based on something computed by our controller. So all of a sudden we will be able to change these seemingly mechanical properties, I mean, they are mechanical, with electronics, with proper control. And to have them change in time, to have them change for different tasks, so we'll have universality. That will be the goal of active compliance. So going back to the PD scheme with gravity compensation, there, if we include terms that will correspond to the effect of the compliance, all of a sudden we get a controllable, a tunable matrix of compliance for our entire system, for our entire manipulator. And in that mathematical model, we have a matrix of compliance that corresponds to our robot. And there exists, out there in the physical world, a matrix of compliance that corresponds to the environment. And you can literally compare the terms in those two matrices, where the manipulator wins in the sense that it has more stiffness than the environment. Well, in those directions of operational space, we can say that the manipulator dominates the environment. In others, it's the environment that dominates the manipulator. So the effect will be where the manipulator is dominant, it tends to get to the position that was intended. So you remember our equilibrium posture. It's going to be achieved there because the environment is going to let it happen. But if the environment is not allowing any of that, if the environment is stiffer than the compliant manipulator we have designed in our control sense, well, there the manipulator will assume the position allowed by the environment. So there will be an equilibrium designed by the environment itself. If there's a wall, it won't go through a wall, no matter that the original idea was for the manipulator to be somewhere beyond that unexpected wall. Again, everything is a spring. Manipulator is a spring, environment is just a lot of springs. Or you can generalize it. I mean, sure, everything is a spring, but everything is also a mass damper spring scheme. So we can speak of not just compliance / stiffness, but also the combination of mass, damping, and stiffness, which is the mechanical impedance. And again, we have the question of doing it passively and doing it actively. In the passive sense, if your manipulator has its own mass, its own damping, and its own stiffness properties that are given by the mechanics of the manipulator, and the environment has those as well in its own model, well then, the whole story of their interaction will be the story of those fixed parameters. And if it works for the particular case, that's grand. It's just that usually it doesn't. So we again have to have an ability to control the impedance, to make it active, to make these mass component, damping component, and stiffness / compliance component changeable. And as it turns out, while compliance control is relatable with the PD with gravity compensation story, impedance control is relatable with inverse dynamics. And since impedance is the generalized resistance to force, all of a sudden we have this new nonlinear force component that needs to be accounted for, on top of all the nonlinearities that we are already handling in our inverse dynamics. So a way to do that is maybe just measure the force and bundle it with the whatever nonlinearities we already have in the model. Well, yeah, but that will deliver you infinite stiffness. So you will always compensate for the whole force that's being exerted on the manipulator. You will never surrender, you will never back off. And that pretty much means that you might be breaking things, you might not achieving your goal, and you don't have the controllability we really wanted here. So you add some active compliance in there. And the result of the whole thing is this whole active impedance for which you can change the parameters dynamically as the control algorithm progresses. Now, what's interesting to note at this point is what exactly happens here if we have disturbance. So if there's a sudden change caused by whatever in the environment, a malfunction of our manipulator, something hitting us where we didn't expect it. As always, we want to be disturbance tolerant. We want it not to stop us from performing our task, and we want to reject that disturbance. And as it turns out, the more you want to reject disturbances and focus on whatever you're doing and be robust to it and keep everything safe, you're getting very compliant. Maybe too compliant even. So one of the solutions is to split the loops. As we thought about it before in the question of achieving the result and being tolerant to the whole disturbance story. Here we can do the same with something called admittance control, which is just a variant of impedance control, obviously, relationship of admittance and impedance, in which we all of a sudden have two loops. One is taking care of compliance to known things, expected things, the real compliance, and the other is just handling the disturbance. All of what we described so far is indirect force control. So we're producing some force, we're reacting to some force, but we're not really doing force control. In the controller is not manipulating the force. Our controller is just manipulating our regular motion stuff. So are we there yet? Can we finally start with proper direct force control? Well, I suppose so, yeah.
Technology is our Lord, given to us by a friend. Pathways of current and sound, hoping to find a bite that's not sure but
So now we want a feedback loop which will collect the info about force and which will perform control over that info. That pretty much means that we don't want to do this sort of control where we don't expect any force to arise. So in the parts of your task that have no interaction with the environment, have no, in those directions that you don't expect forces, don't do force control. Also, do you really want to do PD control on force? You know, when we did PD control on our with gravitational compensation for our regular motion control, P's and D's are performed on the position. So it's position and velocity. And velocity is a pretty decent and smooth measurement, while force usually isn't. There will be a lot of noise in measurement of the force. And as we all know, if you have a lot of noise, the component of a PID controller is just going to introduce a lot of problems, a lot of oscillations, because it changes so abruptly. So we'll stick to inverse dynamics, I suppose. And as it goes with inverse dynamics, we can still think in linear-ish terms. And let's just say, if we have a force loop that is making sure that the desired force is achieved, we can put various different loops inside of that loop, so to make nested controllers. We can put a position loop or a velocity loop inside of our force loop. And sure enough, it does wonders. But what if we don't really want just the force to be controlled, but also the position? So we have a desired value of the force at a particular time instant, but we also have a desired position to achieve at that time instant. Well, fair enough. Do the whole nested loops story again, but introduce the desired position at the same adder where you put in the exact position at that particular time. So where you're closing the feedback on position or velocity. Introduce your position there and see what happens. Now, if you're good with visuals, all of a sudden you may think, but wait, this kind of looks like I'm introducing disturbance. And yes, that is the case. Your extra input of position is a disturbance, and your force loop will, by design, allow it if it's feasible. If it's not feasible, if the force exerted by the environment is just too high, so the environment starts dominating, it will just give up on allowing this disturbance and just keep on holding the force reference, the one that was given by the control algorithm. So it supersedes any position input provided inside of the loop. Now, before we finish for the day, I suppose we should talk a bit about task analysis. That's very practical story of how constraints arise in interacting with the environment, what we can control, what we can't control, and how to model it all.
Don't be afraid, 'cause there
When interacting with the environment, our manipulator has natural constraints along some degrees of freedom, and along the rest of the degrees of freedom, we can impose artificial constraints. Natural constraints are simply what the environment doesn't allow us to do. So we can't have linear or angular velocity along a certain direction or axis, or we can't simply have force or torque along or around an axis. In practical analysis, we first settle these. We first determine what the natural constraints of the system are. And then we can proceed by imposing our own artificial constraints, which are essentially our control algorithms. Take an example of a manipulator holding a box-like element and sliding it along a horizontal surface. It can't get a linear velocity along z-axis if you assume that the z-axis is perpendicular to the surface, because it can't really move into the surface directly. It can't get angular velocity around x or y axis. It can't rotate in that sense. And it's the opposite for the forces. You can't get any forces happening along x or y axis because there's nothing to force against. While you definitely can get a force along z-axis, but you can't get a torque because, again, nothing to have torque against. Think about putting a peg in a hole. You're getting the exact opposite. Now all of a sudden you have an unconstrained motion on the z-axis. You have all the constraints on x and y, so that pretty much puts your forces and torques there, and all the velocities, all the unconstrained velocities along the z-axis. And if you want to make things very complicated for you in sense of what natural constraints might be, think of turning a crank. That one might be a bit hard to visualize, so we might leave it for a more visual medium. That pretty much means that we can finish today's episode of They're Just Robots, and definitely we'll come back to motion and force control, but next time it will be the AI doing it for us, not our regular maths, not our old school control theory and matrices and whatever else, but neural networks. And according to all the sci-fi films, that's a match made in heaven, robots and AI. So, talk next week.
Don't be afraid, 'cause they're made of metal. They still got plenty of heart. You should think of it like it was a garden. There's fruit on the trees and you can pick it. Just don't piss them off, 'cause robots don't stick it. You need some friends and we've got